if you love algebra, this next section is for you. This is about simplifying your integrals before you do integration using long division, short division, or completing the square. So first of all, I want to point out that when you're doing integrals, if you can simplify before you do an integral, then often that makes your life easier. So here are a couple of examples of that. I don't have a quotient rule for integrals, but I can simplify this integral by dividing. Because I'm dividing by a monomial, this would become 17x over 5 minus 2/5. I can think of this as like if it's heart-shaped, break it apart. And so one of the general rules with integrals is do any division and multiplication before you do your integral, if it's possible to do so. So this becomes, I don't need the integral sign anymore. It would be 17 over 5 times x squared over 2 minus 2/5 x plus c. And so that integration was easy as long as I divided first. Same with multiplying. If I can multiply, that makes my integration pretty easy. So I have x cubed over 3 minus 9x plus c. So a general rule, simplifying before you integrate is a good idea. Integration is hard, simplifying is easy. Generally speaking, I usually have to remind people how to do long division. I'm going to start with numbers. So if I want to do 5 goes into 392, I first think, can I take 5 into 3? No. But can I take 5 into 39? Yes. 5 goes into 39 7 times. And so then I do 7 times 5, and I get 35. But really it's 350 because the 7 is in the tens place. So then I subtract, and I do 242. And so then I say, does 5 go into 42? Yes, it does. It goes in 8 times. And then 5 times 8 is 40. And then we subtract, and 42 minus 40 is 2. And we have a remainder of 2, but we can also write that as a fraction of 2 over 5. That's how we do long division with numbers. It may have been a while. It may not have been how you learned division, but it makes long division with polynomials make sense. So x minus 2 is what we're dividing by. We're going into x squared minus 3x plus 1. And so we first look at the x. Can x go into x squared? Yes, it can. So we multiply by x. Oops. And then we take x times x minus 2, and we get x squared minus 2x. And then, just like with numbers, we then subtract. So we have x squared minus x squared is nothing. Negative 3x minus negative 2x would be negative 1x. And 1 minus 0 would be 1. And then we say, okay, does x go into negative 1x? Yes, it does. Negative 1 times. Then we multiply by negative 1, so we have negative 1x plus 2. And then we subtract. And 1 minus 2 is negative 1. So our remainder is negative 1, and we can write that as a fraction, 1 over x minus 2. Right. So the process for long division is you figure out how many times it goes in, you multiply, you subtract, and then you go again. So you might be able to see how that would make integration easier. I don't know how to integrate that, but I know how to integrate all of those pieces. So that's why we are reminding you about long division right now, because it can make your integration easier. So here's an integral with long division. I'd recommend that you try it out and pause the video and then come back, and I'll walk you through it. So pause now. So I'm going to do x plus 1 into x squared minus 4x plus 2. X goes into x squared x times. X times x plus 1 would be x squared plus x. Then I subtract. And I have x squared minus x squared is nothing. Negative 4x minus x would be negative 5x. 2 minus 0 would be 2. Does x go into negative 5x? Yes, it goes in negative 5 times. So then we multiply negative 5x minus 5, and then we subtract. Negative 5x minus negative 5x is nothing. 2 minus negative 5 is 7. And then we can write it as a fraction, 7 over x plus 1. So now we're going to integrate from 3 to 5 of x minus 5 times 7 plus 7 over x plus 1. So that would be x squared over 2 minus 5x plus, oh, there's sort of a u substitution here, but it's a boring one. U is equal to x plus 1, du is equal to dx. So this would be natural log of x plus 1. Oh, not plus c because it's a definite interval. I'm going from 3 to 5. So then I plug in 5, and I have 25 halves minus 25 plus natural log of 6 minus 9 halves minus 15 plus natural log of 4. I am going to just leave it there. I believe that you can simplify that, but we're going to move on. But that's how long division can help you simplify and make it possible for you to integrate. The other tool we can use for making our integrals possible is completing the square. So a reminder about completing the square, when you're completing the square, you ignore the constant at first. You just look at the terms with x's in them and you say, what if they were in a perfect square? Well, if I had multiplied out a perfect square to get those terms, then I would have x squared in this part of my box, if you use the box method. And then the 6x would be evenly distributed in the two diagonal boxes. So the 6x would be a negative 3x and a negative 3x. And then what multiplies to make that? Well, it would be x times x to give you x squared. And this would have to be a negative 3, and so would this. And then if I multiply negative 3 times negative 3, this box down here would be a 9. I meant to change my color so you could see the color. Didn't work. There we go. And so in order to complete the square, I rewrite this so it's x squared minus 6x plus 9 plus 11 minus 9. I haven't changed because I added 9 and then subtracted 9. That is totally legal. It doesn't change my expression. And so that becomes x minus 3 squared plus 2. And that's how completing the square works. I hope that's a reminder and not brand new to you. So if I want to integrate by completing the square, I'm going to look at the denominator here and say, well, that looks like I could maybe complete the square. The reason I'm thinking that I need to use a different method is because when I look at it, I say, well, I can't use long division because the numerator is not a higher degree than the denominator. And I can't use substitution because the derivative of this mess on the denominator would be 2x plus 4, and I don't have a 2x plus 4 that would cancel. So I'm going to try something different, and what I'm going to try is completing the square. So I'm looking at that as I'm ignoring the 5 and saying, well, if it was x squared plus 4x, the 4x would be evenly distributed here, and so this would be x and 2, and this box would be 4. So if I rewrite this a little bit, I have 1 over x squared plus 4x plus 4, and then I have the plus 5 and minus 4. Since I added 4 and subtracted 4, I didn't change anything. I still have the same expression, it's just written slightly differently. So if I group that, I have x plus 2 squared plus 1. And now, because I'm really good at my big 13, I recognize that that's going to look a lot like tangent. So I'm going to make u equal to x plus 2. And and so du would be dx. So if I rewrite that, I have 1 over u squared plus 1 du, and I know how to take that. That would be tangent inverse of u plus c, and u is x plus 2. So this is tangent inverse of x plus 2 plus c. So that is a quick lesson in how to make completing the square help you out. This is a much more challenging problem, so we're going to go through this one. This one, since I'm so good at my big 13, I'm thinking that kind of looks like sine inverse, but it's not perfect. So I'm going to rewrite it a little bit so it looks a little more like sine inverse. So I want to complete the square with my x squared minus 2x. X squared plus 2x. So if I do that, x squared and the 2x has to be shared equally between these two boxes. So it'd be x plus 1. So that means I'm adding 1 and subtracting 1. So I'm going to add 1. Oh, but that's actually subtracting 1 because the distributive, so I'm going to add 1. Double check that that's true, but I've actually added 0 because I added 1 inside of the parentheses, which was actually subtracting 1, and then I added 1 onto the end. So then this becomes 1 over the square root of 4 minus x plus 1 squared. It still doesn't look exactly like sine inverse because that's a 4 and it's not a 1. And sine inverse, that's a 1, not a 4. So I'm going to factor a 4 out of both terms in that square root to make it look more like sine inverse. If you love algebra, today is the best day for you because there is so much algebra today. So I'm taking a 4 out. So this term would become a 1. And this term would become x plus 1 squared over 4. 4 is a perfect square, so I can take it outside of my radical. So I have 1 over 2. And I'm going to rewrite just a little tiny bit differently. I'm going to write this as quantity x plus 1 over 2 squared. Now I'm ready for a u substitution. I'm trying to do a video for my students and you're swearing in the background. So my u is going to be x plus 1 over 2. My du would be 1/2 x. Nope, it wouldn't. It'd be 1/2 dx. And so my dx would be 2 du. So if I do make that substitution, I have 1 over 2 root 1 minus u squared times 2 du. So my 2's cancel. And I'm going up here, sine inverse of u plus c. But again, that's in French. I need to translate it back into English so we can all understand what's going on. So it's sine inverse of x plus 1 over 2 plus c. Okay, it's only fun if you love algebra. But if you don't love algebra and you want some help, please stop by and see me. I love to talk about algebra and math. This lesson is also assigned on Khan Academy. Thank you. Bye. So my children want to say sorry about the swearing.